Imagine a cluster of supercomputers, right? They're running this massive petabyte-scale physics simulation. But to pass the results to the next time step, they're forced to summarize everything they just did, using only a string of emojis.
I mean, it sounds completely absurd when you put it like that.
Right. But that is exactly what standard large language models are doing right now. And honestly, it's why we're skipping the usual preamble today. Welcome to AI Paper Slop.
We are getting right into it today.
Totally. We're doing a deep dive straight into a paper that fundamentally rethinks how autoregressive models process information. It's called Full Bandwidth Transformer by researchers from Johns Hopkins, Princeton, and Microsoft.
And this is a big one.
It really is. So for anyone listening who trains or serves LLMs, here is the 60-second summary to get us started. Standard autoregressive transformers suffer from this massive bottleneck that we really rarely talk about. It's a narrow vertical channel.
Yeah, that vertical starvation.
Exactly. During decoding, a model compresses a massive, d-dimensional top-layer hidden state all the way down to a single discrete token before feeding it back into the bottom layer.
Which is just throwing away so much context.
Right. So this paper introduces what they call latent feedback decoding. It feeds the entire top-layer continuous state back into the next step. 0 architectural changes, less than 1% inference overhead, and it allows a 200 billion token model to match the performance of models trained on up to 1 trillion tokens.
All while generating significantly shorter reasoning traces, which is just, it's wild.
It's incredible. So let's unpack this.
Yeah, it's a brilliant framing of a mechanical limitation that we've all kind of just accepted, you know, like the cost of doing business with transformers.
Yeah, we just assumed that's how it had to be.
Exactly. But to really appreciate the problem they're solving, we have to look at the discrepancy between the horizontal and vertical axes of a transformer. Because horizontally, like, across the sequence of generated tokens, dense attention gives every single token full bandwidth access to the entire past.
Right, because of the KV cache. Like, if the model is generating token 500, it can just directly query the keys and values from token 2.
Yeah, it has this rich, continuous representation of the whole history mapped out in high-dimensional space.
But vertically, it's a completely different story.
It's strictly depth-frozen, meaning through the depth of the model layers, a state produced at, say, layer L is only readable by the layers above it.
Okay, so if the network computes some really nuanced representation of, I don't know, semantic uncertainty at layer 12.
Layer 4 of the next token's forward pass cannot see it. That computation never loops back to the bottom of the stack.
Wow. So the only way information from the top actually makes it back to layer 0 for the next step is through verbalization. It has to be squeezed through that vocabulary bottleneck.
Right. You're taking this continuous space, which is often, 40, 96 dimensions or more.
Yeah, easily.
And that space represents this vast landscape of probability mass, alternative phrasing, latent reasoning, and you're forcing it through an argmax or sampling operation just to get one single discrete token.
You're literally bottlenecking the communication channel to the log base 2 of your vocabulary size.
Exactly. All that non-verbalized computation is essentially left behind in the KV cache. It's locked at the specific depth where it was originally computed.
So going back to that supercomputer analogy, forcing that massive computing cluster to communicate via emoji, it means it has to use a ton of emojis to get any complex point across.
That's a perfect way to put it. This vertical starvation is exactly why standard models are forced into using chain of thought.
Oh, because they need a scratch pad.
Yes. They literally have to use generated tokens as an external scratch pad just to carry intermediate state forward to the next steps.
That makes so much sense. That's the mechanical reality driving model verbosity. So how do they fix it? Talk to me about the technical implementation of this latent feedback.
Right. So the full bandwidth transformer widens this channel through what they call, latent feedback. In standard decoding, your input at step t is just the embedding of the token you sampled at step t-1.
Sure, standard autoregressive generation.
But in latent feedback decoding, the input for step t is a fusion of the new sampled token's embedding and the top layer hidden state from step t-1.
Okay, so we are routing the continuous state right back into the ground floor.
Exactly.
But wait, I want to push back on the specific architecture they used for this fusion, because the authors use a gated linear unit, right? A GLU.
Yes, an asymmetric GLU.
Why not just use an additive shortcut? Like, ResNets taught us years ago that identity mappings and simple additive shortcuts are the holy grail for gradient flow. Literally just adding the token embedding to the hidden state seems like it would be dramatically easier to train.
You'd think so, right? The resonant intuition totally makes sense on paper. But in this specific autoregressive training environment, an additive shortcut is actually a massive trap.
Really? How so?
Think about the training dynamics from the model's perspective. It's just trying to minimize loss with the least amount of effort possible. If you give it an additive shortcut, the model can easily learn to push the weights applied to the dense hidden state straight to zero.
Oh, I see. It just takes the path of least resistance.
Exactly. It can entirely ignore the continuous state, rely purely on the discrete token embedding, and just comfortably hit the standard pre-training loss curve.
Without ever actually utilizing the new wide channel, it essentially chooses to remain a standard depth-frozen transformer.
Yep. So the asymmetric GLU forces the issue. They designed it so the continuous hidden state sits on the value pathway, but the discrete token embedding acts only as a multiplicative gate.
Okay, so if the model decides to discard the hidden state,
It discards the input entirely. The discrete token's identity only survives in the d-dimensional gating pattern that it imposes on the continuous state.
oh wow, so that makes reading the dense state mandatory, not optional. You are physically forcing the network to keep that continuous channel open.
Exactly. And because this fusion preserves the standard input dimension, D, the serving cost is basically negligible.
I was going to ask about that. It's just, what, a rounding error in terms of compute?
Yeah, we're talking about 2 D by D matrix multiplications per generated token. You preserve the standard KV cache layout. You preserve all the standard attention mechanisms. The VLLM serving stack barely needs any modification.
Okay, so inference is incredibly cheap and mechanically simple. But looking at the training setup, I have a big question. The autoregressive nature of this loop, doesn't it completely break the parallel teacher forcing that makes transformer pre-training even physically possible on modern GPUs?
Ah, yeah, you've hit on the core engineering hurdle of the entire paper.
Because in a standard setup, you process, say, 4,000 tokens simultaneously, right?
Right.
Because position T only depends on previous tokens, which are already known in the training data.
Right, but if the input at position T now depends on the completed forward pass of the hidden state from position T minus 1.
You're back to training an RNN. You have to unroll it sequentially. How are they training this without the compute cost just going to absolute infinity?
You're totally right. You cannot unroll a sequence of 4,000 tokens sequentially during pre-training. It would literally take years. So they solve this using a multi-pass training objective that leverages temporal parallelism.
Okay, temporal parallelism. Walk me through the mechanics of that.
Basically, they approximate the recurrence using Jacobi-style updates. In the first pass, you compute the forward pass standardly across all tokens in parallel using only the plain token embeddings.
So you just pretend the latent feedback loop doesn't exist for a second.
Exactly. And that gives you your first set of top-layer hidden states, like a rough draft of the sequence context.
Okay, so pass 1 is just standard teacher forcing. Got it.
Then for pass 2, you take those top-layer hidden states from pass 1, shift them 1 position to the right, fuse them with the original token embeddings using that GLU, and rerun the whole stack in parallel across all positions.
Oh. And then you just repeat this for K passes. So I'm paying for sequentiality across the number of passes, which is just a tiny integer, like 2 or 3, rather than across the sequence length of thousands of tokens.
Right, and the gradients are still flowing backwards across positions because pass 2 uses the shifted outputs of pass 1.
It is really clever.
And the scheduling heuristics here are vital to making it computationally viable. They don't actually do this multi-pass routine for the whole training run.
Really? When do they introduce it?
The bulk of early training is just standard 1-pass. They only introduce 2-pass batches really late in the training process.
Which means you could start from a standard off-the-shelf pre-training checkpoint and just warm up the latent feedback loop.
Exactly. It makes it so much more accessible to train.
Okay, I understand the computational trick.
But
I have a major concern about extrapolation here.
okay, lay it on me.
If the model is only unrolled 2 or 3 times during training to save compute, what happens at inference time? Like, when I prompt this model to write a Python script, it might generate 1,000 tokens. If the recurrent state has only ever been practiced for 2 steps, I would fully expect the math to explode. Doesn't the hidden state just compound tiny errors and turn into infinite numerical garbage by token 50?
It's a completely valid concern, and the authors actually mapped out this exact extrapolation collapse. If you only train with 1-pass and 2-pass batches, the model does diverge at inference.
Okay, so it does break.
It does. The validation loss spikes, the recurrent hidden states oscillate wildly, But the fix they discovered is what we can call the 3% magic.
I'm sorry, 3%. What does that mean? If 97% of the time the model isn't practicing a deeper loop, how did the 3% inclusion prevent the math from exploding into NaN values?
Well, let's look at the math of dynamical systems. To prevent a recurrent loop from exploding, the learned feedback map needs to be a stable contraction toward a fixed point.
Meaning the Lipschitz constant of the transformation needs to be bounded.
Precisely. And they found that mixing in just a tiny 3% fraction of 3-pass batches acts as a powerful regularizer.
Just 3%.
It's 3%. It teaches the network how to handle a state that has already been fused and passed through the network once before. That tiny exposure is enough to force the optimization landscape to bound the activation growth.
That is genuinely fascinating. It basically learns the geometry of stability just from glancing at the third step.
Yeah, it turns the feedback loop into a stable contraction. Though they do deploy a few lightweight tricks to guarantee that stability holds for over 1,000 generated tokens.
Like what kind of tricks?
Well, they use depth scaling, which artificially scales down the residual connections in the deeper layers so the hidden state norm doesn't naturally grow too large.
Makes sense.
They apply an RMS norm on the fused input to strictly bound the variance before it hits layer 0. And crucially, they added jitter noise to the carried state during training.
Oh, jitter noise.
Right.
What does that actually accomplish mathematically?
It acts as manifold smoothing. By injecting a tiny amount of Gaussian noise into the dense state before feeding it back into the GLU, you force the model to tolerate slightly shifted or imperfect recurrent states.
So instead of memorizing a fragile exact trajectory, the model learns a robust neighborhood of valid states.
Exactly. If errors compound slightly during generation, the jitter noise training ensures the model knows how to pull the state back to the center of the manifold.
Okay, there's one more distribution shift I'm curious about. At inference time, you process the user's prompt using standard token embeddings, right? But then you suddenly switch to these fused hidden states for the generation phase.
Right.
That boundary seems like a jarring transition for the model's internal activations. Doesn't it freak out?
That's where the prefix mixin comes into play. During those multi-pass training batches, they randomly revert the beginning of the sequence to plain embeddings.
Oh, so it simulates the exact prompt then generate boundary the model will encounter in the real world.
Yep, ensuring the layer 0 attention heads don't freak out when the latent feedback suddenly kicks in.
Okay, so we've built this beautiful computationally free loop, and the stabilizers keep the hidden states from blowing up. But engineering aside, does wider channel actually result in a demonstrably smarter model, or just a more complex one?
Oh, the empirical payout is massive, but it's highly dependent on how you actually deploy the latent feedback at inference.
Okay, break that down for me.
The researchers defined 3 distinct regimes: standard, soft, and fused.
Let me guess, standard is just normal decoding.
Yeah, you ignore the latent feedback entirely. Then soft decoding processes the prompt normally, but activates latent feedback during the token generation phase.
Okay, and fused.
Fused decoding is the heavy hitter. You do an extra latent feedback pass over the prompt first, and then proceed with latent feedback generation.
Wait, so fused decoding basically lets the model marinate on the prompt in its continuous latent space before it even outputs the first token.
Exactly. And the performance boosts from that marination are stark. If you look at standard LM evil accuracy, a 200 billion token full bandwidth model approaches or directly matches the performance of standard models trained on up to 1 trillion tokens.
1 trillion. That is a 5x improvement in data efficiency.
It really is.
You are basically buying a permanent baseline upgrade just by tweaking the input bandwidth. But looking at the benchmarks for you listening, there is a very clear divergence in how the model behaves on different tasks.
Yeah, it's a fascinating split.
Because soft decoding gives the absolute biggest gains on math benchmarks, like Math 500 and GSM-8K. But fused decoding gives the biggest gains on coding benchmarks, like human eval. Why the split?
Well, let's think about the cognitive requirements of those 2 domains. Math is fundamentally about state tracking across intermediate steps.
Right. When you're solving an equation, your logic evolves as you generate the answer.
Exactly. Soft decoding allows the continuous draft space to carry that evolving logic forward step by step.
Whereas coding is heavily front-loaded. Like if I give a model a prompt with 6 nested constraints for a Python script, and it doesn't perfectly understand how constraint A interacts with constraint F.
The code is doomed from character 1.
Right. So fused decoding gives those prompt states an extra round of continuous refinement.
Exactly. The top layer understands the global context of the prompt, passes that high-level semantic understanding back down to layer 0, and the network essentially rereads the prompt with the benefit of hindsight before it ever commits to an action.
That makes total sense. And this continuous reasoning space leads to an incredible side effect in the actual output the model produces. We talked earlier about chain of thought being a crutch because of the vertical bottleneck.
Right.
When you widen that bottleneck, the inner voice of the model fundamentally changes, doesn't it?
It is perhaps the most profound finding in the entire paper. On Math 500, base models using soft decoding achieve higher accuracy with significantly shorter median reasoning traces compared to standard decoding.
I want to make sure you listening catch this. It is achieving higher accuracy while generating fewer tokens. Can you give me a concrete idea of what that looks like?
Sure, imagine a standard model tackling a GSM-8K word problem. It has to write out, if John has 5 apples and gives 2 to Mary, we must subtract 2 from 5. 5 minus 2 equals 3. John has 3 apples.
It forces every single intermediate step out into English text because its vertical channel is starved.
Exactly. But a model using soft decoding might just output, John has 3 apples.
It's literally doing the math in its head. It doesn't need to write down the intermediate subtraction because that computation is securely held in the high-dimensional continuous vector propagating through the latent feedback loop.
It is fully utilizing a continuous draft space. But there's a tragedy here regarding how we currently train models.
Oh no, what happens?
The moment you apply standard instruction tuning to this beautiful, concise model,
The conciseness vanishes, doesn't it?
it completely disappears. Because standard instruction tuning datasets are built on human data or chain of thought data generated by other standard models.
And that training data is aggressively verbose.
Highly verbose. So fine-tuning forces the full bandwidth model to abandon its efficient continuous reasoning and go back to thinking out loud, token by tedious token, just to minimize the loss against the verbose training data.
It is like taking a mathematical savant who can solve complex equations in their head and aggressively punishing them until they agree to show their work using crayons.
That's sadly accurate.
But before we explore the implications of that tragedy, we need to talk about the physical proof the authors provided. Because they didn't just look at the shorter text outputs and guess that the model was doing internal reasoning right. They actually looked inside the network using linear probing.
Ah, yes. The layer 0 telepathy experiment. It is a fantastic piece of analysis.
Walk us through it.
They set up these synthetic state tracking tasks where the correct answer depends on information presented hundreds of tokens earlier in the sequence. With standard pre-filling, if you probe the residual stream at layer 0 of the final token, it operates at near chance accuracy.
Because it has absolutely no idea what the global state is due to that depth-frozen vertical constraint.
Right. It requires multiple layers of forward processing just to pull the relevant state out of the KV cache.
But the moment you allow one recurrent pre-fill step,
With just one step of latent feedback, a layer 0 probe can predict the global state tracking with near 100% accuracy.
oh wow,
Yeah, the global context has been fully injected into the shallowest layer of the network.
it is literally teleporting the fully processed conclusion back to the starting line. Layer 0 goes from being completely blind to having the answer key before it even fires its first attention head.
It proves mathematically that the continuous channel is not just an abstract theoretical concept. The network is physically routing high-level semantic aggregates from the deep layers back down to the primitive feature detectors.
Allowing the early layers to make globally informed decisions right out of the gate. So the core trade-off we are looking at here is incredibly favorable. We are spending slightly more compute during mid to late training with those multi-pass Jacobi updates.
Right.
And in exchange, we buy a permanent, practically free upgrade in pre-training data efficiency and inference capability. We fix the vertical starvation of the transformer without having to abandon the attention mechanism or the KV cache architecture that the entire industry is built on.
And it leaves us with a fascinating and frankly provocative puzzle for the future of AI alignment.
Which is?
If latent feedback naturally allows for hyper-efficient, concise, continuous reasoning, but our standard instruction tuning violently overwrites it to make the model act like a verbose human, how do we build entirely new on-policy reinforcement learning pipelines?
Oh, I see. We need RL pipelines that actually reward the model for utilizing its dense inner voice, rather than punishing it for not showing its work in English.
Exactly. We have to stop forcing the supercomputer to speak in emojis.
That represents a massive paradigm shift for how we are going to generate preference data moving forward. For you listening, take a hard look at how your current fine-tuning pipelines might actually be lobotomizing the latent capabilities of the models you were training. That is all for today's deep dive into the full bandwidth transformer on AI Paperswap. We will see you next time.